Here is a combined summary of the 2 pages. The proposed approach, FewShotNeRF, addresses the challenge of generating novel views of real-world objects with limited multi-view images through meta-learning-based novel view synthesis. This method utilizes meta-learning to acquire an optimal initialization, facilitating rapid adaptation of a neural radiance field, NeRF, to specific scenes. The focus of the meta-learning process is on capturing shared geometry and textures within a category, embedded in the weight initialization. This approach expedites the learning process of NeRFs and leverages recent advancements in positional encodings to reduce the time required for fitting a NeRF to a scene. Neural Radiance Fields, NeRF, have emerged as a transformative technology in novel view synthesis, particularly in the context of posed multi-view images. However, this enhancement comes at the expense of increased computational costs. To construct a NeRF capable of generating novel views, each scene necessitates the initialization of a new model from scratch, followed by training via volume rendering using 2D supervision provided in the form of multi-view images. Researchers have explored 3 main approaches to inject prior knowledge into NeRF models, including conditioning the NeRF model on a latent code, learning a prior initialization, and using diffusion generative models. However, these approaches have limitations, such as limited expressivity due to the constraints imposed by the code's size or reliance on 2D priors. In contrast, gradient-based metalearning approaches maintain the full expressivity of NeRF models, enabling the representation of any scene that can be captured by per-scene optimized NeRF models. The proposed method aims to apply gradient-based metalearning to NeRFs that incorporate view-dependent color output, with the objective of achieving generalization in many categories of commonly used objects. Significant modifications have been made to the architecture of NeRFs to enhance their efficiency, including the use of task-specific, learnable data structures and multi-resolution hash encoding functions. The introduction of the hash encoding function has ensured convergence with a significantly lower number of iterations, further optimizing the training process. The paper aims to make 3 significant contributions: utilizing hash encoding to accelerate the metalearning process, conducting extensive experiments on categories of real-world objects, and investigating the efficacy of metalearning in acquiring a 3D prior and generating novel views independently. Here is a combined summary of the 2 pages. Novel view synthesis, NVS, involves generating new viewpoints of a scene from a set of input camera images. Recent advancements have utilized 3D representations within neural networks, requiring fewer input images. However, these methods necessitate multiple camera views for a single scene, resulting in lengthy training times. To address this, a recent work introduced an approach capable of training a model within a few minutes. This study investigates NVS using a limited number of training samples, utilizing this approach as the base model. Metalearning is a machine learning paradigm that involves pre-training a model to acquire the ability to learn efficiently. Model-agnostic meta-learning, MAML, and reptile or optimization-based algorithms commonly used in metalearning. Gradient-based metalearning employs outer loops of stochastic gradient descent, SGD, to learn an improved initialization, enabling fast convergence when faced with new instances of the same task during testing. This research aims to apply metalearning to learn the initialization of view-dependent neural radiance fields, NeRFs, and evaluate its performance in a challenging setting. NeRFs synthesize realistic 3D scenes by directly learning volumetric representations from 2D images. To render images from NeRF, it employs ray marching, casting rays from a virtual camera and integrating radiance values along the ray's path. The proposed approach, FewShotNeRF, learns additional priors implicitly from the weights of the NeRF model. This method relies heavily on the understanding of NeRF and metalearning. The approach is rooted in the concept of metalearning for initialization, dynamically adjusting the initialization by shifting it closer to the optimal parameters derived from NeRFs fitted to various scenes within the same category. The study conducted a comprehensive evaluation of 3 prominent metalearning algorithms: Reptile, first-order MAML, and second-order MAML. Reptile emerged as a compelling choice due to its favorable computational cost and efficient training process. The algorithm's performance is governed by the equation theta equals theta plus alpha, theta, meta minus theta, where theta represents the initial model parameters. Theta, meta is the meta-learned model parameters, and alpha is the meta-learning rate. The evaluation highlights the trade-offs between computational efficiency, memory consumption, and meta-training adaptation steps. The results demonstrate the potential of meta-learning for NVS, particularly in scenarios with limited training data. In the realm of machine learning and computer science, the development of novel techniques for accelerating the learning process of neural radiance fields, NeRF, has garnered significant attention. This paper presents a new approach, dubbed FewShotNeRF, which leverages metalearning to enhance the efficiency and adaptability of NeRF models in real-world scenarios. The proposed method is designed to address the challenge of generalizing NeRFs, particularly in resource-constrained environments. The authors employ a PyTorch implementation of instant NGP as their backbone model and adopt the reptile metalearning algorithm due to its suitability for their context. They conducted a comprehensive evaluation using the publicly available Colorado 3D dataset, encompassing real-world multi-view objects. This dataset provides essential components, including relative camera poses for each frame and masks that delineate the object of interest from the background. The evaluation protocol involved comparing FewShotNeRF with several existing approaches, including PixelNeRF, NeRFormer, sparse fusion, and others. The results demonstrate that FewShotNeRF outperforms most of the comparisons and performs on par with sparse fusion, while not relying on any external models. The authors also conducted a thorough evaluation using 150 scenes, calculating averages for each quartile to provide a nuanced understanding of their method's performance at 25%, 50%, 75%, and 100% of the scenes. The authors systematically evaluated 3 distinct metalearning algorithms, ultimately selecting Reptile based on its favorable computational cost. They conducted a comparative analysis between their method and related approaches, employing quantitative metrics including peak signal-to-noise ratio, PSNR, and structural similarity index, SSIM. PSNR quantifies the absolute likeness between the reconstructed view and ground truth, while SSIM evaluates the structural similarity between these views. The experimental results show that FewShotNeRF achieves competitive performance compared to the state-of-the-art approach, sparse fusion, without relying on any external models. The evaluation protocols are slightly different, and the evaluation is more robust and stronger than a random sampling of 10 scenes. The author's method demonstrates the distinct strengths and capabilities of their approach within the context of the Colorado 3D dataset. In the realm of metalearning, this research paper presents a comparative analysis of 3 algorithms: Reptile, MAML first order, and MAML second order in the Apple category. The findings indicate that Reptile outperforms MAML first order with the same number of metatraining iterations, while MAML second order achieves competitive results with significantly fewer iterations, demonstrating its efficiency. This highlights MAML second order's ability to achieve comparable performance with reduced metatraining steps, challenging conventional approaches. The paper also discusses the results on CO3D, showcasing quantitative outcomes under diverse input view scenarios. In a 2-view setup, the proposed method performs better than NeRFormer and is competitive with 45, without using an external prior such as a diffusion model. The 3-view and 6-view setups yield further improvements in results, suggesting that the meta-objective captures strong inner loop priors to the outer loop. Moreover, the study examines how image quality improves over several iterations of metatraining. The results display a clear and consistent trend, with an increase in PSNR values with more metatraining iterations, indicating a continual improvement in image quality. This underscores the reliability of the findings and the effectiveness of iterative metatraining in enhancing image quality. The paper introduces FewShotNeRF, an approach to generalize neural radiance fields, NeRFs, for view synthesis with few input views. It makes 3 significant contributions: utilizing hash encoding to accelerate the training of NeRF models in the inner loop of metalearning, conducting extensive experiments on real-world object categories to evaluate the effectiveness of this method, and scaling the metatraining to over 300 scenes to distill the 3D priors into a single model. These experiments provide valuable insights into the feasibility and potential benefits of using hash encoding for meta-learning NeRF models. The proposed method relies on learning 3D priors only from the meta-objective without relying on external models. In conclusion, the presented findings have the potential to shed light on NeRF generalization. The utilization of hash encoding for meta-learning initialization, along with the extensive experimental evaluations, contributes to the advancement of generalizable NeRFs. Future work could further refine and extend the proposed methodology by exploring additional enhancements and could also focus on applying FewShotNeRF to more complex and challenging scenarios like dynamic scenes. The referenced papers provide a comprehensive overview of the current state of research in computer vision, machine learning, and neural rendering. Figure 4 illustrates the qualitative progress achieved in novel view generation across 4 categories, showcasing the model's ability to enhance realism and accuracy. The references cited span a wide range of topics, including light field rendering, metalearning, implicit neural representations, and neural scene representation. Notably, papers 1, 19, and 20 discuss the use of neural radiance fields for view synthesis, while 4, 5, and 14 explore the application of transformers and implicit neural representations for image and scene modeling. The work of 9, 11, and 26 focuses on metalearning and online learning methods, highlighting the importance of adaptability and task-agnostic learning in computer vision. Papers 2, 6, and 24 discuss the use of metalearning for few-shot learning and task adaptation. The references also touch on the topic of 3D reconstruction in scene representation, with papers 16, 17, and 22 discussing the use of neural sparse voxel fields, adaptive coordinate networks, and continuous signed distance functions for shape representation. Furthermore, the references highlight the importance of datasets and evaluation metrics in computer vision research. Papers 3, 7, and 27 discuss the use of large-scale datasets, such as ShapeNet and common objects in 3D, for training and evaluating computer vision models. The cited papers demonstrate the rapid progress being made in computer vision and machine learning, with a focus on developing more efficient, adaptable, and accurate models for image and scene understanding. The references provide a valuable resource for researchers looking to explore the current state of the field and identify areas for future research. In the realm of machine learning and computer vision, the concept of neural radiance fields, NeRF, has garnered significant attention for its ability to rapidly acquire a scene's understanding with a few images. This paper explores the efficacy of metalearning in enhancing image quality within the context of NeRF, specifically focusing on the impact of view count on image enhancement quality. The paper begins by discussing the importance of scene representation networks, which are continuous 3D structure-aware neural scene representations. It highlights the work of Sitzman et al. 30, and Sitzman et al. 32, who introduced the concept of scene representation networks and implicit neural representations with periodic activation functions, respectively. These advancements have led to the development of novel methods for optimizing coordinate-based neural representations, as demonstrated by Tanchik et al. 38, and Tanchik et al. 39. The paper then delves into the concept of metalearning, a technique that allows models to learn how to learn from other models. This is exemplified in the work of Vilalta and Drisi, 41, who provided a comprehensive perspective and survey of metalearning. In the context of NeRF, metalearning enables the model to rapidly adapt to new scenes with only a few input images, thereby enhancing image quality. To evaluate the effectiveness of metalearning in NeRF, the paper presents a comparison between metatraining with 3 views and 6 views. The results, as shown in Table 4, demonstrate the model's capacity to excel in scene comprehension without reliance on external models. The reported PSNR values underscore the efficiency of metalearning in enhancing image quality, particularly noteworthy for its ability to achieve substantial improvements even with a limited number of input images. Furthermore, the paper discusses various metrics used for image-based comparisons, including PSNR and SSIM. These metrics are calculated using equations 6 and 8, respectively, providing a quantitative measure of the model's performance. The paper also references other relevant works, such as Joe and Tulsiani, 45, which distills view-conditioned diffusion for 3D reconstruction, and Yu et al. 44, which introduces PixelNeRF, a method for generating neural radiance fields from one or few images. In conclusion, this paper highlights the potential of metalearning in enhancing image quality within the context of NeRF. By leveraging the capabilities of scene representation networks and implicit neural representations, the model can rapidly adapt to new scenes and achieve high-quality image synthesis with minimal input. The paper's findings underscore the importance of optimizing coordinate-based neural representations and the role of metalearning in advancing the field of computer vision and machine learning. The table on page 13 presents a comparison of peak signal-to-noise ratio (PSNR) and structural similarity index (SSIM) values obtained through metatraining using 3 views and 6 views, without dependency on external models. The results are reported for various scenes, including donut, apple, hydrant, vase, cake, ball, bench, suitcase, teddy bear, and plant. The table demonstrates the impact of varying view counts on image quality enhancement by selecting the top quartiles from the evaluated scenes. The results show that increasing the number of views from 3 to 6 generally improves the PSNR and SSIM values, indicating better image quality. For example, the average PSNR value for the top 25% of scenes increases from 23.43 to 26.45 when using 6 views instead of 3 views. Similarly, the average SSIM value for the top 25% of scenes increases from 0.783 to 0.797. The table also highlights the variability in performance across different scenes. For instance, the hydrant scene shows a significant improvement in PSNR and SSIM values when using 6 views, while the bench scene shows a relatively smaller improvement. These results suggest that the effectiveness of metatraining with multiple views may depend on the specific scene being evaluated. The transition to page 14 is not provided, but based on the context, it is likely that the next section will discuss the implications of these results, potential limitations, and future work. The authors may also provide additional analysis or visualizations to further illustrate the impact of varying view counts on image quality enhancement.